Thank you very much, Paul. So please stay on the line. We are going to take questions during the panel discussion for all the speakers together at the end of the session. So you're going to stay on the line, is that right?
Correct.
Okay, thank you very much, Paul. Great. So our next speaker is Dr. Yang Liu. So you can start coming up. While you're coming up, I'll just say a couple words. Dr. Liu is a professor at University of Illinois, Urbana-Champaign, and also the deputy director of the Center for Label-Free Imaging and Multiscale Biophotonics. It's got a cool acronym. If you spell that out, it's CLIMB, C-L-I-M-B. So I love that. I'm going to let you go ahead. So thank you very much.
Thank you. Great to be here. This is such amazing community. It's my first time here. I want to thank Kevin for inviting me and all the organizers putting together such a wonderful event. So I think for this audience, I don't really have to talk about the importance of looking at biological systems in multiple scales. We have wonderful sections on super resolution microscopy and nanoscale structures. We also have sessions on organ level imaging. The important thing is these days you not only look at them separately, but also putting all of them in one system. So you can get visualized molecular structures in a large context of tissue microenvironment. And the same goes to the time scale. Some process happen really fast. Some may take hours, days, or weeks, or even months and years to develop. The challenge is lots of short time scale event. You don't know when that happens in the long course of the process. So it's critical to capture those critical events at the right time. So it's a challenge problem for microscopists to be able to follow process over a long period at high temporal resolution. So my lab actually work on a wide variety of technologies. So we develop label-free quantitative phase imaging. We also spent many years working on super resolution microscopy, especially single molecule localization base. We improved their throughput. And in recent years, I got interested in sort of connecting this to connecting the scales from mesoscale, millimeter systems level to nanoscale. So we put everything along looking at on one samples. And also besides the spatial temporal resolution, content is equally important. So we also spend quite a bit of time developing various imaging approaches, probes, protocols to map tens of proteins on the same sample. So today, because this section is on sort of live in action, so I feel I need to talk about probably the best techniques that you can do live cell imaging, which is label-free, because we always worry about the potential perturbation to biological function. And if you don't put label there, they have minimum perturbation. So the quantitative phase imaging really has advanced dramatically in the past decade. Many of you probably seen those booths, from TomoCube. So that's from my colleague, Yang-Kong Park. He's done a wonderful job getting the system into the commercial systems. So the quantitative phase imaging has now gone to much higher throughput, much higher resolution. When you visualize unlabeled samples at high resolution, that really give you a lot of information. And also get to 3D and deeper tissue. And one of the criticism we often get is you don't have the specificity, you don't have the content. And with the help of AI, now you actually can do this through image-image translation or virtual staining to render lots of the functional information into the label-free image. So today I'm going to focus on one aspect, which is the higher throughput. So if you use a traditional microscope, you typically will have some trade-offs. If you want to see lots of cells at the same time, that means you're going to lose some resolution. If you want to see finer details, That means you're probably going to use high NA lens, high magnification, so you're limited to the number of cells you can look at simultaneously. The same trade-off goes to sort of the nature of label-free. You don't perturb any functions, but you don't get lots of the molecular information. So you can monitor cells over a long period. You can observe many dynamic information, but they are limited in the molecular content. So this is still a hard problem. To address partially, one strategy we thought about is if we go outside the traditional microscopy, we go to the astronomy. So if you look at, this is a picture of a galaxy, it's an enormous spatial scale. And this is, you don't even use too fancy of optics. So those amateur astrophotographers actually can take it with a little bigger lens than we normally use. And also a camera is typically tens of millions of pixels. They are not actually expensive. So even amateur level people, they can purchase this and take those beautiful images. So we thought if we can leverage those inexpensive optical components and put it in a microscope setting, we could potentially increase our throughput. So that's basically a system we put together. We use a stereo lens, stereo microscope. So those are off-the-shelf lens. And we put together with a camera. And the whole system is very, very simple. So it's essentially a bright field microscope coupled with the fluorescence imaging capability. What you can get is, so this is a single field of view, roughly 2 by 3 millimeters, a snapshot single field of view. And you get roughly 3,000 cells on this. If you zoom in a specific area, you actually get subcellular details. You can monitor the cell dynamics, really looking at some of the finer features over time on thousands of cells. So you can do quantification. So in phase imaging field, we like to look at, for example, how how cells respond to the drug treatment. And this is a chemotherapy drug 5FU. You see the changes in cell morphology. The morphology changes slows down responding to the drug. And this is the dry mass. So this essentially the phase volume. We calculate from the quantitative values of phase, and you can see because slowdown of cell growth, and you can see how the dry mass also slows down in those treatments. So people use it for drug screening applications with this approach. And just give you a little bit of, for those of you not familiar with how the phases get, it's actually a very simple approach. So we just take a few stacks. So it's a stack, typically 5 frames. Just take those bright field images, and you can retrieve phase through this defocused image. So in theory, you just need 2. And the intensity gradient is dependent on the changes in intensity in different axial directions. So we use this so-called, it's a decade, it's been well established called transport of intensity, or TIE-based phase retrieval. And you can get, it's very computationally very fast because we operate that in the Fourier space. So you can retrieve phase with this approach. And so these sort of just give you ideas when you monitor cells. This is a single field of view. You literally can just put in the tabletop incubator and look at it over time. So this is when the cell density is low. And you can look at it over several days. There's just so much information you can get when you look at all the cells. You can see the finer dynamics. This is day 3. You see the sort of the colonial expansion, right? The colony in the neighboring, they start to put together. If you go further, you see when the cell become more dense, condensed, and you see lots of cells dying. Let me just see if I can zoom in. Can you play the movies? Click. Yeah, so I just give you an idea of the resolution you can get. You still see a lot of finer dynamic. You see the filament, how they move at the edge. And if you watch these cells very quickly, and you see they die, you see the blabbing. So it really is so much information you can get. It's a very simple system to set up. And just sort of get to more biologically relevant questions. So this is the one of the power using this approach, because you can capture so many cells at the same time. You can detect those rare events. So this is a, can you play that movie? I think this was played earlier. So you can see these cells actually sort of get fused with the bigger one. But it's not done yet. Once they get in, you see they quickly divide. So you see how the spindle aligned, and then they divide. So this event, some people call it cell in the cell or polyploid cells. So we saw over about 5 hours period, we saw maybe 3 such events for thousands of cells. So this sort of thing, I lots of times interested in observing this, but I think for biologists that's not sufficient. What that means molecularly. So what we did is we pushed further, look at the same cell population. We basically fixed them, and then look at did the multiplex fluorescence imaging to get a better understanding of the molecular characteristic. So one thing we found is these cells, they have very high level of stemness, CD44, and they actually have, I'm interested in chromatin, so they have lots of, actually has higher DNA content, higher proliferation. So that indicates this kind of mechanism make the cell more aggressive. And you can also look at this in 3D. When you go to higher resolution, this is the image of a spheroid. And you can really get single cell level. And these are bright areas are the lipid, and these are the individual nuclei. And you can see really the single cell nucleus, see a lot of the single cell information in this large spheroid. Just to give you an idea, this is a correlation with fluorescence. You can better understand the contrast, and then we do the virtual staining essentially through this way. And here, just give you an idea of the difference between the drug sensitive and resistant cell types. So you can see a lot of heterogeneity. The dark area is actually the nucleus. So allow you to gain lots of understanding in 3D system as well. Just conclude, we have developed this ultra high throughput QPI, so you can look at the cell behavior with subcellular details. And what is really powerful is not just the QPI alone, it's really the capability to combine morphology with the molecular structure. We also use super resolution to further look at these changes. So I spent 15 years in Pittsburgh before I moved to Illinois about 2 years ago. So these are my group at Pittsburgh, part of the work done there. And then these are my new group, and some of the newer data, I think half of these are done at Illinois. Here are my contact. Thank you all for your attention.